Great. Okay, well, all right, it's good to see everybody here today. Thank you for joining. Before Maya introduces our speaker today, who is Chris Brown, I just have one quick announcement, which is that next week we will be having a seminar. I'm afraid we put together the schedule before WPI shifted the course, the term schedule. So Tony Seba will be joining us. He is originally from Stanford. He'll be talking about the economics of disruptions, the focus on energy, transportation, and food and agriculture. So it should be an interesting talk. Yeah, it's difficult to reschedule people at this point. So I'll let Maya go ahead with your introduction.
Okay, thank you. Hello, everyone. We're excited to have Professor Brown for our talk today. I know I've been using their lab facilities a lot, so I'm glad to have the opportunity to make this introduction. Professor Brown is currently a professor in mechanical engineering here in WPI. He has studied in University of Vermont, and his dissertation is on chip formation during machining. After his studies, he has worked on engineering surfaces at Lausanne's Swiss Federal Institute of Technology until 1987. There he has originated multi-scale geometric texture analyses. He also began working on his discrete interaction model for topographically related phenomena. He worked on process and product innovation as a senior research engineer at Atlas Copco's Europe Research Center for 2 years. After that, he joined mechanical engineering faculty at WPI in 1989. 2 years after joining in 1991, he founded WPI Surface Metrology Lab. This lab currently has Mars stylus instrument and a Sensovar confocal, which I use and know that's amazing. In collaboration around the world, WPI has measured and analyzed food, teeth, dinosaur footprints, archaeological artifacts, pavement, skin replicas, and many kinds of additive surfaces. Professor Brown co-founded the International Conference on Surface Metrology at WPI, and he has published over 150 papers on surface metrology, design, manufacturing, and sport engineering. He has patents with many of his students on characterizing surface texture, friction testing, and sport equipment. His algorithm for topographic analysis are used worldwide in science and engineering research. It's a pleasure to have you as our speaker, Professor Brown. I'll hand it to you from here.
Okay, Maya, thank you very much. That was very nice and plenty long. All right, so now I got to find out where my slides are. I just had them open. Where did they go? Here we go. All right, I'm getting it. Can you see my slides?
Yes.
Okay, good. You'd think I would have this down by now, wouldn't you? All right. So thanks for this opportunity. And I know I've spoken at this venue before. I like to have the opportunity to tell people. We've got new people here, and actually people have joined us from outside WPI, and that's really nice. Thank you all the way from France, where I'm going to be in a week. Anyway, so today I'm concentrating more on really theory and almost philosophy on how we should be understanding topographically related phenomena, as opposed to the results of particular work that we've done. And there's all kinds of topographies at all kinds of scales. On the left, we see here micro electric discharge machining, or a surface from that. And on the right, we see the moon. And we notice there's some similarities. There's sort of a bunch of craters. It's neat to see the commonality in surfaces across a wide range of scales, from nanometers to kilometers. And we've been fortunate to be able to study those on all kinds of things. My email is here at the bottom. If you have some questions and we don't have time for them at the end, please send me an email. So Maya did a great job of mentioning my other areas of interest, but I would like especially to note about axiomatic design, because that was part of the inspiration for this work. And back in around 1980, Nam Su from MIT proposed two design axioms. Most people don't think there should be any rules for design. And he went to see what two things, or what things, not just two, but what things might be in common for all good designs. Nam's first honorary doctorate is from WPI. So we've got some close ties with him. I've been working recently more on engineering ethics, and it's disappointing to know how many people don't even know the first canon, which is shown here: hold paramount the safety, health, and welfare of the public. And so sustainability and revitalization come naturally from that. And had engineers held paramount the safety, health, and welfare of the public, our climate wouldn't be in the lousy shape it's in right now. We couldn't have gotten there without a lot of technology. Whether or not it's engineering, since it doesn't hold paramount the safety, health, and welfare of the public, is something that we need to discuss. Sports engineering, the main thrust has been injury reduction through nonlinear spring systems, and then manufacturing. And I was lucky to be around when the stars aligned and we were able to bring in 21st century machine tools into the WPI manufacturing labs. I was all excited about what we were doing with topographic research years ago, and I was having lunch with my advisor at a meeting in Paris. And I was talking about this, and he interrupted. He says, "What is a surface?" So, and what is a topography? And okay. So we need a definition. So I've got here a cross section of a surface, aluminum with some oxide, and then so this is in a TEM. So you have to put another layer on it. We did some of these in Lausanne. I couldn't dig up one of the ones we did though, in time for this. But so what we're looking at is a very thin region with high gradients and some physical property, which we can see here in the transmission electron micrograph of this thin film. I haven't had a chance to do any of these since I was in Switzerland, but doing this perpendicular to the surface at the surface is a chore, and we were able to do some of that. But the topographies, okay, this is the geometrical aspect of the surface, and that's what we're going to be characterizing. So to talk about it at all, as Lord Kelvin pointed out, we need to be able to measure it and quantify it, and that's where it gets interesting. So, and we can only measure it by some interaction with a sensor. Lots of times you say, well, that's not the real surface. You get, then what is the real surface? If you can't measure it, I don't think we can talk about it. So, but the way we usually measure it is heights as a function of position. Of course, now with CT scans, we're getting more than one height as a function of position, and reentrant, we're looking at voids, and it's getting more interesting, but that's a good subject for another day. So traditionally, most of the time we're looking at linear profiles, and that's still largely done in industry. And what we're looking at here is a turned surface, and we can see the cusps that result with each feed mark and each revolution. And then down below, we're looking at what we might call an aerial profile that shows the surface in what metrologists call 3D and physicists like to call 2D. But anyway. But here's some things that we need to keep in mind sort of philosophically. We can't know all the heights on the surface. And we can't know the height at a point. A point is too small to measure. There's no reaction with a surface at a point. So we need to measure the height in some finite zone or region. And we move over and measure it again. So here's the profile, and there's the instrument that measures the profile. And there is a little, you can't quite see it, but there is a little stylus on the end of this thing. And this is an inductance transducer that translates the movements here to heights. basically the same technology as we used to use to listen to music. So the interesting thing, I think, that makes this particularly challenging and rich for investigation and study is the irregular components. And all surfaces tend to have irregular components at sufficiently fine scales. They're surfaces, so they should be continuous, but not always. The topographies don't have to be differentiable. But our ISO standards, that's International Standards Organization, for those of you who are used to WPI speak and think it means in search of, but the ISO standards treat the topographies as if they're continuous, using the very best 18th century mathematics. I'm starting to make some progress on the committees, and that may change. But so there's a little illustration of the kinds of irregularities that we see on surfaces. So, whoops. What should be surface topographies? I spent a long time working on these, but I'm pretty good at missing stuff. So continuous, smooth, or complex, random, differentiable. So fractals was a model I started off with, continuous but nowhere differentiable. And that's a neat mathematical model, but we've stopped using that term and dealing more now with irregularity. There are a lot of fractal purists who question whether or not it's appropriate to use fractals on this. So we've been calling it multi-scale geometric characterization is what we're doing. But here's the interesting question, I think, for lots of things that we do, not just surface metrology, but and lots of technical things that we do in engineering, particularly. Is it an experiential discipline or scientific discipline? So an experiential discipline, obviously based on experience, standards, best practices. And we got a ton of standards for surface metrology and all kinds of people talking about best practices. So certainly we're in there as an experiential discipline, but can we be a scientific discipline? And a scientific discipline is distinguished from experiential by having a few simple self-consistent laws or axioms. And these can be used to solve or understand a wide variety of problems. Understanding in the technical sense means being able to solve problems. So the scientific disciplines exploit the compact nature of our universe. So it's much easier, for example, to describe things with a few scientific principles than lots of experience. And therefore, they are easier to learn and to apply. So axioms. So we don't often deal with these. Euclid sort of took this on a little while ago and dealing with mathematics. But so regarded as being established, accepted, self-evidently true. And I'm going to make a stab at that in surface metrology in a moment. And they're the basis for argument or inference. And then corollaries, and I'm going to take a stab at this. These are inferred from the axioms. So let's take a look and see what we can come up with. But first, I want to set a context for this. So how does surface metrology create value? What's the value proposition here? And I would say finding strong correlations so that we could correlate the topography we get with the processing conditions, and that we can correlate the performance of the surface, things like friction, adhesion, heat transfer, with the topography. So these are the correlations, and there's sort of two kinds we talk about. The first kind from processing, and the second kind to performance. Confident discriminations. So lots of times the task is not to set up a continuous kind of correlation kind of thing, but just say, can I tell these apart? And that's a problem that comes up actually quite frequently in industry and technology. And adequate reproducibility. So, I mean, currently these are used for quality control, facilitating commerce. I specify certain surface eruptions on something, and the supplier sends me the parts, and I check it, and they get paid when I agree that the parts meet the specs. But getting the topographies with the process and performance that I just talked about, and that supports product and process design. And then monitoring processes. Can we keep a manufacturing process in control by monitoring the surface? Because basically in manufacturing, we're trying to get, for mechanical parts anyway, the surface we want, where we want it. And then for like degradation, when do I need to replace something because it's wearing out? Degradation or infrastructure. We've got lots of experience with decaying infrastructure in the United States. And then for scientific discoveries, things in fields like anthropology and archaeology. Okay, surfaces cover everything. They are essential to heat and mass exchange for things like energy capture, storage and conversion, and for carbon capture. So they're quite relevant to the issues we're having currently with sustainability and revitalization. All right, on with it. Axioms. Axiom 1. So topographically related phenomena result from discrete fundamental interactions that occur at certain scales. So if we're thinking, for example, and this is sort of how I got started on this about 40 years ago in Switzerland, thinking of adhesive strength being due to a bunch of individual bonds, which I've tried to illustrate here with a bunch of circles. So anyway, so it's not a continuum. I can't divide the surface forever and still have adhesion occurring. I get down to the size of a bond. Now, then there are naturers. Naturers should be not without the R, sorry. Natures of the discrete interaction. I'm terrible at proofreading. I got to write down here. All right. So there's a causal geometric nature to the interaction. So contact phenomena, like I'm trying to illustrate with this little cartoon here. So we're looking at how are these asperities interacting? Maybe liquid layers are there, maybe they're shearing off, but there is some fundamental interaction here that's occurring that then contributes to the overall behavior. So we've got the scale and the nature. Now the scale stuff is, and this idea that we've got discrete interactions, this is not a new idea by any means. The atomists back in Greece, and it's Democritus, something like that, who was in there before Euclid, and he looked at the concept of an atom. And so things are not infinitely divisible, and we don't have intrinsic wholes, but aggregates. And all the depictions of him, he looks rather jolly. And I think the reason is that the other thing he's known for is this quote on happiness. Not in possessions, not in gold, happiness dwells in the soul. So no wonder it looks like he could be Bacchus. And he's been having a good time with a bottle of wine. All right. So just to get back to this discrete interaction and the nature. So if we're looking at adhesion, which was sort of my one of my early things on this, is we've got macroscopic strength is equal to totaling the strength of individual bonds here by some number, individual bond strength, and then dividing by the overall area. So we get the strength of a single interaction, total projected area. And then how many single interactions do we have? Well, that depends upon how much area we have at the scale of the interaction. So one of these interactions indicates what the scale is, and that's to the axiom 1, and the nature of the interaction is the strength. So then all right, I was distracted by the poll, sorry. want to make sure everybody's here. Okay, and so but they might not all be active. Maybe they're in too steep a valley or something, or there's some contamination, or the chemistry isn't right there. So we've got a fudge factor that will be less than 1. And then so we total up the area. And what we end up with is the overall strength of the interaction, substituting and rearranging, is the strength of a single interaction divided by the area of the single interaction. So that is the interaction. That is the nature. That was the axiom 2. And this is taking care of the scale. And that was axiom 1. So there's a model for adhesive strength. Not the axioms, it's more the axioms were based on that than that was based on the axioms. So we developed this way of determining the relative area. The area at some particular scale is a ratio to the projected or nominal apparent area. And that's actually, we got a patent on that with some students at WPI, and now it's in the national and international standards. Actually has been for quite a while. And it is marketed by Digital Surf as a module you can get from Mountains Map. And they actually support the lab with a gift whenever they sell one. And now, one of the interesting things about the relative area is that it can be related to the inclinations on the surface. So we're looking at sort of surface slopes, or a spatial derivative of the heights. And so we have this little tiling exercise we have in the algorithm, and the alignment wasn't maintained too well through copying these things over, but there it is. But anyway, so we have the projected area, and that's a little derivation to show us that the relative area is related to the slope here, 1 over the cosine of theta. And it's a special kind of weighted average. As this gets very steep, it has less weight. So we could look here, I've forgotten what this surface is, but I use this for illustration. And you can see it's got some quite jagged features on it. And the average inclination at a very fine scale is quite steep. And then as we get to larger scales, the average inclination declines quite a bit. So this is generally true. When an ant walks down the sidewalk, the ant is climbing over cliffs and things that we can just ignore as we walk down the sidewalk with our big feet. So corollaries, measurements. So the measurement resolution, because we can't talk about the topography unless we measure it, as we established. So there are discrete, we have to include the discrete interaction scales, and then meaningful samples of the topographic features that where these interactions are occurring. So, and in general, we don't know what those scales of interaction are, and often we're doing, part of the objective of our work may be to determine what those scales of interaction are. So we use multi-scale characterizations and analyses to test for the fundamental scales, and I'll show you some examples of that. And the other thing is surfaces, if we zoom in enough, they're heterogeneous, meaning that if we take a small enough region and look at it in different spots on the overall surface, or sample that, we see that there's variation. Think of a road. So if you're sampling at a small enough area to get on a piece of aggregate in the road pavement, you're going to see a lot of variation as you get from one kind of aggregate to another, and the binder and so forth. But if you take a big enough patch, 150 by 150 millimeters or something, then it's going to appear pretty homogeneous when I sample it in different places. So anyway. So here's an example of the traditional way of measuring things. It's a contact stylus profiler where I was able to find the trace I left in the SEM. This is difficult to find in a scanning electron microscope, but it was neat in Switzerland. We had all the time, and back in those days, all the Polaroid film we wanted. The Swiss do a nice job of supporting their technical schools. So what's the scale here of interaction? Well, it's based on how the tip is engaging, and it samples the heights more than the valleys. And people go, oh, well, that's not a real representation. It is. And for contact mechanics, that might be just what you want to measure. And this is, widely used, particularly in things like the auto industry, because the contact mechanics will probably be more severe than what we're looking at here. And this gives a good representation. And is the kind of measurement that I think still, well, anyway, internal combustion engines were developed with that kind of measurement. Now, if we take a closer look at the measurement, so we can't measure the height at a point. So the instrument samples some sort of region, and we tend to think, oh, a light instrument, that's going to be much better. Light interacts with the surface in different kinds of ways. Sometimes it's reflected, sometimes it's absorbed. And when I try to measure with light, I'm using like confocal or interferometric or focus variation. All three modes are available on the Sensiphar in our lab. Or maybe some sort of reflectance, and that's available on the gel site that we just got. So those, but there's a lot of software to interpret the way the light's coming off the surface for the different measurement modes. And that's usually proprietary software. So don't make the mistake of thinking, oh, it's light, so it's better than the stylus. It depends upon what you're doing. But in any event, so we can sort of see too, the interactions here, three possible interactions between the sampling interval, which is I measure a height and then, or sample a height and move over and sample it again, and the sampling width, and then how big a region did I measure? This is actually some French, special French paper from the art museum that we measured for them. Anyway, corollary 2, statistics. So we want the appropriate kind of statistical characterization, because there's different things. For example, if we're looking at crack initiation, like fracture, fatigue kind of things, it's going to be extreme values and the variance. But if we're looking at friction or adhesion, it's probably going to be average. So use the right kind of statistics, and that's corollary 2. So here's an example. And this was a collaboration with ENS, what was then Cachan, and is now Saclay, Paris-Saclay in France. Margot Valouz came over and worked with us one summer. She was a graduate student there. The names in red are undergraduate students from WPI that all collaborated on this. These are two professors from Cachan, Saclay now. And then this was one of their graduate students who did all the hard work of breaking all these things in fatigue, which is a lot. Anyway, so this was looking at sort of the correlation strength as a function of scale. So very quickly, the surface was milled a couple different ways and directions, and then some of this was stress relieved and some wasn't. And so a number of different surfaces were created, and we can see there's renderings of a couple of measurements colored by height, so we can sort of see the differences in the surfaces. So we developed, and this was largely Matt Gleason's work, this method according to Heron. So far, I just realized this is the first citation I have after the birth of Christ. So anyway, this is a way of figuring out curvature discretely across the surface at a location. So the curvature varies with scale and location on the surface, and that's what this is showing us here. So we've got scale and position, and then curvature here vertically and colored, and we get these nice pretty diagrams showing us the differences between two of the surfaces in these kind of curvature maps. And at the largest scales, of course, the 3 points that we use to calculate the curvature are far enough apart so we can't calculate very many of them. And then at the finest scales, we get lots, and we can see all that little rippling and things kind of, there's some neat patterns on that. We haven't studied that yet, but those, I think there's a lot there. The fatigue tests, of course, are extremely fatiguing. That's why we use the same word. And so to find the fatigue limits, you got to break a lot of stuff. And so as the stress goes down, the number of cycles go up, and then you figure out where the fatigue limit is. And then we looked for correlations between, now these are different statistical treatments of the curvature, because the curvature varies with position and then with scale. So here's the scale over here. And here's how at that scale, we're taking care of the statistics. So maximum curvature, the mean of the 10 maximum curvatures. So we're trying to get a little bit more of a blend in there. Then we've got maximum curvature plus, or maximum, sorry, mean curvature plus standard deviation of the curvatures. And every time we're trying this, we're thinking, all right, that's pretty good. I mean, if we look at the literature, we don't find anybody else in this kind of experiment that's getting R squareds of 0.76. So, you know, we should have said, well, all right, we're pretty happy. Maybe we should take the rest of the summer and go canoeing and hiking. But we thought we could do better. And then we did. And so here is the blend of statistics that got us there. Exactly why, and could we have predicted this before we started? I don't know. But anyway, this gives us an R squared of 0.96. Looks like we cheated. And there it's attached to a certain scale. So the statistics, I mean, most people would just use average height, and there's no correlation at all. So that's that achieved a very good result, and the value is in the strength of that correlation. So there's the regression curve, and I can't remember, I think these two were heat treated. So in this case, the topography is more important than the residual stress. Now, as we noted, these surfaces look a bit rough, so I'm sure the residual stress will be more important as the topography, as there's less topography. And here's the way the R squared, the correlation coefficient. So what we did a lot of these correlations at different scales. And then I wonder if this thing can move someplace. I hope that wasn't in everybody's way. All right, so it wants to be over there or something. Anyway, we have a lot of these correlations at different scales. And then this was at 610 micrometers. And then we plot the R squared value versus scale on the next slide. So here's R squared, there's the scale. And the thing that's impressive here particularly is that there's a very narrow region in scale where we get a very strong correlation. So that if you're not using multi-scale and you have not included that scale in your analysis, you might conclude that topography isn't that important in this. And so you have to look in that, you have to look at the scales. So there it is. So here's another example. Actually, I just submitted a revision of the paper, and we'll have to wait and see if they were happy with that. So friction on snow and ice, and that's been one of my favorite things because I was doing sports before I was doing engineering. And it was essentially engineering that got me into sports. Sports that got me into engineering. And so the ski snow friction is quite interesting. There's, and Sam Kobeck, who was at the U.S. Army Cold Regions Research Engineering Laboratory up by Hanover, New Hampshire, near Dartmouth College. He was one of the experts and has written a treatise on this, and I was fortunate to have had lots of discussions with him about this. And so his sort of theory was that you build up a liquid layer between the ski and the snow. And If there's not enough, you get this dry plowing, so the friction's a little bit high. If you get too much, you start getting capillary adhesion or capillary suction, like the same sort of action that makes wet clothes stick to you. But if it's just right, sort of Goldilocks, we get the lowest friction coefficient. So somehow we want to prepare our skis. So what is the fundamental interaction here? So this is sort of building on Kobeck's thing. And so he's hypothesizing that it's these little ligaments, perhaps, wetting. So this is like water between something here supposedly representing, I guess, an ice crystal. So liquid water, and then like the base of a ski. So you've got this little attachment. And so by the wetting properties of the two, this sort of tells you what the angles there are going to be and how difficult it's going to be to separate it. So the idea is that to actually separate this, you've got to create more liquid surface area that has a higher energy than the liquid solid areas, so that you have to do work to create that extra surface. So this is sort of what the base of the ski looks like. And that's just some measurements we did here at WPI to see if we could actually differentiate them. And then here's our triangular tiling example on that. And then on the ski work we were doing, here's a droplet. And so you measure this angle here, theta, which I've used for other things in this talk, I'm sorry. But so you have a droplet and the surface tension's pulling it into and gravity or you have this nice smooth shape here. But notice when we get near the surface, so here's the ski base, it's irregular. And so my thought is that there's little facets here and there's some natural contact angle based on the chemistries of the water and the base that it's happiest with, and it finds these little facets and starts off with those at the water or liquid, solid interface there. But then once you get away from that, the surface tension and gravity take over for the shape and smooth it out. Because all of these little things here make for more surface energy trying to maintain those, and the droplets, of course, want to be roundish to minimize the surface energy. So there's also, we could go to an even finer scale and look at molecular dynamics simulation. So this is something about liquid atoms piling up on a surface, and there's you can find a lot of these in the literature. I didn't look too carefully. I just wanted a nice illustration here to show that you can actually take a look at atomic forces and sort of pile the atoms up one at a time and figure out what contact angles from the chemistry might be as well. So we've done some wetting work at WPI, and this was in conjunction with the Center for Advanced Research in Drying, or CARD, and this was sort of directed by Professor Daniello, and I'm just tagging along. And I've presented some of this before, but now we have another context for this. And so here we're doing multi-scale geometric analysis. This is relative area. So the polymer surfaces that we're measuring the contact angle on are prepared by molding them against abrasives. And so here's the grit size and the abrasive. So we've got 7 different grit sizes there, so that we've got a variety of surface topographies to test against. Now, in a moment, I'm going to show you where the strongest correlations are and how we got those. But if we just take a look at the ranking here, it doesn't look like they're going to correlate very well with anything, because these seem to be all over the place. Anyway, so this is how the relative area is changing with respect to scale. So the smallest relative area you can have is 1. And in this case, 1.75 is really a pretty big relative area for a lot of engineering surfaces. So here we're looking at the complexity. So the complexity is essentially the slope of the area scale curve. So this is the area scale. So if we look at sort of the slopes, and then we take the slope over a certain little scale range, about a decade, but we can do it in a sliding fashion. So we get a continuous thing here. It's related to the fractal dimension. But anyway, so here is the region where we're getting the strongest correlations. And so when we look at the grit, the ranking of the grits in this region of strongest correlations, it ranks perfectly. So the 400 are the biggest grits and the 3,000 are the finest. And so there's kind of a thing here, because when we first presented this, we just had the grits with the colors off in the corner. And I don't like presenting it that way, but I didn't have time to fix it. And so for this, I started fixing it. And I noticed that, look at that. These things that were sort of a mess before in this region of strongest correlation rank perfectly. So here is the R squared using now the complexity from the previous slide. And here's the region where they correlate the strongest. And so we're way up there, approaching 0.99, which again looks like we're cheating. The neat thing is, though, to look at the way this trend goes, and has some similar things to what we just saw. If we're at too large a scale, the correlations aren't good. Here, I think we get funny looking correlations just because the relationship is so weak and we're dealing essentially with flat lines. There's not much slope to it. We actually did develop another representation where we included the slope, so these things sort of disappear. But so these are unimportant, but I include them because we had that whole range of scales. And so these sort of line up by chance a little bit. And but then look at this, it just pretty steadily increases right up to almost 0.99. And so here is a scale range, and the highest is at 0.58 micrometers squared. So on this surface, for these things, this is the scale of the interaction. And the nature of that interaction is trying to find an angle. And that's, anyway, so there we are. So to summarize, here we have a topography that we want to study. And so there's something that was done to prepare it. So here it was the ski base preparation. And then we have some sort of preparation scale or processing scale. So this might be like a manufacturing process, but it also could be wear. It could be artistic, it could be painting, it could be micro dental wear on the teeth of animals that we can analyze and tell what they were eating. Anyway, so there's the processing scale, then the performance scale. Here we're looking at friction because it was the ski bases. There's the topography. We measure it, as we saw the certain scales, and the measure, as we do the measuring, we get the measured data, and then we get analysis scales and statistics here. And we talk about the first kind, to prepare the surface, and the second kind on the for the performance. And so the topography goes from the dependent variable in the first kind to the independent variable in the second kind. And so those are the regression analyses and discrimination tests, or the statistical stuff. So in summary, I've proposed some principles and trying to capture the compact nature of topographically related phenomena. So we have this idea that there are discrete fundamental interactions at a certain scale with a certain character or nature. And to understand these, we have to measure appropriately and use the right kind of statistics. And of course, we have to characterize the right scale and the right nature or character. So, and a couple of acknowledgements. One, I'm grateful to WPI for paying me my salary over all these years. And then the students that I've had in Switzerland, France, through many collaborations there and in the United States have been wonderful. And I couldn't do this work without them. And then the Card Center has given us support, and that's was directed the wedding work. Professor Daniello, who he must be fantastic. He sold wedding experiments to the Drawing Center. And Digital Surf, they make Mountains Map and Besançon. We've been working with them for quite a while, and they give us some software to use. And as I said, one of their modules has the area scale analysis. Sensifar from Barcelona, Spain, gives us a beautiful SNEOX measuring microscope for us to use. MAR used to be MAR Federal. Federal used to be down in Providence. And they gave us a contact stylus profilometer. And I forgot, and I really want to apologize to my good friends at GelSite. This is a remarkable instrument, and that would be worth its own presentation at some point. But and one of our collaborators from our lab has gone to GelSite to work, which is wonderful. So anyway, thanks to those. My apologies to my friends at GelSite, because their instrument opens up lots of things that we can do. So and measure that we couldn't measure before, because we can take the measurements wherever we go. All right. Thank you very much for your kind attention. And here on the left, we have some trees that no longer exist. These nice carbon capturing, oxygen producing organisms have been replaced by a building that absorbs oxygen and emits carbon dioxide. What a trade.
Thank you very much, Professor Powell, for a great presentation.
You're welcome.
Okay, we now open the floor up to Q&A, so feel free to unmute yourself or have your hand raised.
This would probably be a good time to take another quiz to see who's still awake or who's off getting a cup of coffee. I see not too many people with their cameras on. But lots of people are still here. That's nice.
We have a few minutes and can talk now if you want, Professor Brown, but I'd understand if you...
No, Randy, this is our question period. Thanks for thinking of that, Randy, but not now. Please follow my earlier instructions. Email me and we'll set something up.
Are you free later today?
Email me. We'll see. Tell me when you're available, when you'd like to meet.
Okay. Bye.
So I do have a question, Dr. Brown. This is Sarah. So your definition of surface would be like the interface between two metals. You would consider that a surface?
Sure. Yeah.
Okay.
It could. We could even talk about precipitate in a metal.
Okay. I get. Okay. I mean, that makes sense. I guess I just like, I don't know. I always thought of the, the surface of something where it's contacting, air. But okay, interesting.
Yeah, I mean, it could be. The boundary between two gases gets harder to define. It's harder to keep it to a thin region, but certainly the boundary between two liquids could be possible too. Liquid solid, air solid, and then you've got all kinds of things like when you've got lubricated sliding friction, where you've got two solids and a liquid, and air probably as well.
Interesting. Okay.
Hi, Professor.
Oh, go ahead.
Yeah, Jason.
So just a quick question. So remember the graphs you showed before of surface roughness as a function of position and then length scale.
Yeah.
So I was wondering so on the end of that, the length scale axis, right? How do you determine the position? Is that at the center of the window, or is that on the left edge of the window, or the right edge, or how do you?
Yeah. Okay. So yeah, no, good question. So let me see where so we choose 3 points that are equally spaced horizontally. There are other ways of doing it, but this is, and there are some cautions with this. And so when we look at these, the window here is extending actually from one side of this to the other, basically. And here the windows are smaller and sliding over it. Does that answer your question?
Yeah, sort of. So what about like where maybe like 3/4 or almost to the end, right? So maybe you have 4 or 5 windows, right? So would it be the centers of those windows, or would it be?
Oh, yes, right. The position that we're recording there is the center. So that would be the spatial position of Z2 as I'm showing it here.
Okay, all right.
And so the problem is, as you move it side to side, Z1 and Z3 tend to fall off the side of the surface. So that limits what you can do.
Okay.
So if you needed more data at that scale or more curvatures, you just have to do a bigger measurement, and you can stitch measurements together now, and that's actually quite easy to do on the Sensifar, and it's very fast.
I have a question for you. First, sorry that the poll distracted you for a moment there, but you mentioned fractal dimension a couple of times, and I wonder if there are properties that you have found or macroscopic behaviors that correlate better with fractal dimension than with some of the other types of metrics that you talked about, the curvatures and other things.
We looked hard for that. That was sort of the theory, because I started on this in the 80s, and actually, at that time, when you did a computerized search for the term fractal, you could actually order all the papers. And then that went crazy. And I don't know what's happened to it. I've stopped following it.
Okay.
But we were certainly hopeful that the fractal dimension was going to correlate with something. The one time that we saw that was on cracks in ceramics in a Canadian nuclear power reactor. That's the only time, but the fractal networks make sense. The problem is, we kind of saw on the complexity scales that the fractals vary with scale, certainly, on natural surfaces. Where we see the big ranges of scale that, like 6, 7 orders of magnitude, it's things like clouds. But when we look at a machine surface, zoom out a little bit, it looks like whatever we intended it to be, a cylinder or something, right? We zoom in and we start seeing the machining marks. We zoom in, we see something else. So the complexity of the surface, which the fractal dimension would indicate, changes with scale. And that upset some of the mathematical purists. And so it sort of takes it outside that realm. So we decided to call it something else. But a lot of people, we started off calling it fractal stuff, and the physical anthropologists, paleontologists still use the term fractal.
Okay, terrific.
Okay, I think we can end the Q&A here because I know everyone has classes and meetings at 1. I put Professor Brown's email in the chat for any further question. Feel free to reach out to him directly. And thank you everyone for joining. Thank you, Professor Brown.
You're welcome. Thank you all for listening. And please email me with questions.
Perfect. Right. Thanks again. Right. Great seeing you. Bye-bye.